Yeah. Yeah. So welcome again to our joint seminars. And today we are very happy to have Anupam MAZUMDAR as the speaker. Well, we know that even if there are many things to say about Anupam, but let me just briefly remind you his career. Anupam received his PhD from Imperial College, London in United Kingdom in 2000. And during 2000 and 2002, he was a postdoctoral fellow at the ICTP Trieste in Italy. And between 2002 and 2004, he was a Canadian Institute for the Theoretical Astrophysics National Fellow at the McGill University in Canada. And throughout 2004 and 2007, Anupam was an assistant professor of the Nordic Institute for Theoretical Physics in Copenhagen in Denmark. From 2007 to 2017, he was a reader at the Lancaster University in the United Kingdom. During 2008 and 2013, he was an honorary associated professor at the Niels Bohr Institute at the University of Copenhagen in Denmark. In 2015, Anupam was awarded with the Japan Society for the Promotion of Science Award. Since 2017, he has been working as an associated professor at the von Swinderen Institute at the University of Groningen in Netherlands. Well, there are actually many things I know, but Anupam has made several fundamental contributions to different branches of physics, and today he will talk on the spin entanglement witness for quantum gravity. Anupam, thank you so much for accepting our invitation.
Thank you very much, Suat, for your kind invitation, and it's really my pleasure to talk to all of you. I could see some of my old friends as well, which is very nice. I see them after a long time, virtually, so it's very, very nice to see them. Let me share my screen. So I hope you can see the screen now.
Yeah, we can see.
Good, thanks. Okay, excellent. So let me talk about a topic which is slightly different, because I know that maybe one of your main focus is towards quantum gravity. And but I think we all agree that when it comes to quantum gravity, maybe one thing which perhaps we are missing, or we are perhaps severely requiring, is to have an experiment through which we can engage with. Like, LSC has done to phenomenology, and we have seen how phenomenology has exploded since 2000 or late, even before. The phenomenology has become such a wonderful subject, has engaged so many young people. Of course, it would be very nice if we have something similar for gravity as well, or testing quantum gravity. So this is the question which I would be trying to understand and try to explain, and it's called witnessing quantum gravity via entanglement of masses. So, the point is, the bottom line is that the question is, what exactly really leads to the attraction between the two neutral masses, and what is its origin? Is its origin classical or quantum? And if it is quantum, can I devise an experiment through which I can test this hypothesis? And so this is the question which we will be focusing on today. And so I actually started this work way back in 2017. Before that, I was not in this field. Since 2017, I have become more and more focused towards the testing aspects of quantum gravity, and started with one of my very close collaborator, Bose. And you can see the first paper where, besides me and my colleague Bose, who comes from quantum information side, the rest of them are experimentalists and working in quantum information, quantum technology. So it's very interesting to see how gravity and quantum information, these two subjects, have come so close to each other. And hopefully, maybe not in 5 years' time, but 10 years, 15 years' time, hopefully maybe some very exciting experiments one can do in a laboratory, in a tabletop experiment. And that has led to many collaborations. Many people got involved. And some of the papers, so I will be focusing on the first paper, 1907, and the first paper of 17. And then I will talk about a paper which will appear tomorrow with some of my students and colleagues and collaborators. Martina Schutt is there, she's in our group, and Marco Torres is from Glasgow, he's also present here. So some of them are present today. And there are other papers along with our talk. And around the same day, on the same day, there was another paper. So there was sometimes very interesting thing happened. The same day, there was another paper came in talking about something very similar. But I request you to both look into both the papers and see the details, what's there and what's not. So when it comes to quantum gravity, it's fair to say that even as a subject, it's very interesting. Just the pure theoretical aspects, very interesting. There are many ways maybe people can think about. And this is just to show you that, if you are blind and blind men touching elephant, depending on which part of the elephant you touch, you interpret it accordingly. So, and there's no dearth of quantum gravity proposals. Out of all these proposals, maybe in the low energy limit, the most low energy limit is perhaps the perturbative quantum gravity. Around a fixed background, you're perturbing the metric and trying to quantize that metric. And that dates way back from the days of Sujan Gupta, 1950s, then Feynman, and then Kibble, and then many stalwarts, Deser, many people have contributed to this story. So, my focus will, of course, not be to test extreme non-perturbative aspects of quantum gravity, but to test the most humble, which is something which, those who don't believe in quantum gravity also will say, okay, maybe this is the first thing you would like to test. So perturbative quantum gravity. So this is the thing which perhaps I would like to address. So the vision is that. Sorry, is there a question? Maybe. No. Okay. So witnessing quantum gravity in a tabletop experiment. So this is the this is the vision which we want to test it. But what we would like to do at the end of the day is to create a very tiny accelerator. And the concept of accelerator will come in very soon. It's almost like, Higgs factory, or here we are calling it like a graviton factory where we can excite the gravitons. So this is what we will like to see. And so when we talk about quantum gravity, so the couple of things which we borrow from quantum mechanical system is the quantum. So if you say that gravity has to be quantized, it means that the geometries have to be in a quantum superposition. It's like Schrodinger cat state. You want to create a Schrodinger cat state. And then you would like to see the existence of this hypothetical particles spin to massless graviton, which mediates between the two neutral masses, like photons are mediating electromagnetic interactions. Similarly, graviton, we believe that it mediates this gravitational interaction. So the plan of my talk is to introduce you this QGEM. And as I said, that I would like to create in laboratory this Schrodinger cat state. So the cat is alive and dead simultaneously. So it's a quantum superposition of geometry, the operator valued interactions, which will become clear once the talk gets progressed. And so what I will do is that I will introduce you the QGEM protocol. I will talk about the how to read the witness. And then there are many challenges. We don't want to shy away from the challenges, because whenever you want to do experiment with gravity, there are many challenges. And then if time permits me, then maybe one can motivate even quantum gravity from experiment, like what we have seen in LHC, that experiment somehow motivates even theory. So the collaborators, some of my collaborators are already here present, young collaborators, but some of them have been listed them. So it's pretty international. People are coming from mostly from all over the world. Melbourne is from Australia. Few people are from Israel. Ron Follman's group who are doing the experiment from Israel. Gavin is from UK, and Bose is my colleague, longtime collaborator, who has been working on these aspects with me. So what would you like to have? You would like to, when you talk about witnessing quantum gravity, you would like to have a bona fide test. When I say bona fide, what it means is that something which cannot be replicated by classical system or classical physics. Now, when it comes to astrophysical imprints, and this is such an old subject, many people have been trying. I mean, there's no dearth of people have been attempting to understand this question way back from the days of even Feynman. So now people have thought about astrophysical imprints, like changing gravitational, gamma ray bursts, changing the photon dispersion relationship. And also there are, B mode coming from the gravitational waves in the primordial power spectrum, tensor modes essentially. So there are many ways people have been trying to put constraint on the nature of gravity, nature of quantum aspects of gravity. But all these astrophysical or cosmological issues, they have either some astrophysical uncertainties or there are cosmological uncertainties, because many times we don't know even the early universe. We make some assumption based on the assumption we try to work on. So the question you can ask is that how well have we checked even our assumptions? So there are many problems there to say directly that we have witnessed the quantum nature of gravity from these experiments. So at the end of the day, you would like to have some kind of very razor-sharp argument, a sharp witness. You would like to have an experiment, perhaps, which is like your LHC, where you can repeat the experiment many, many times. You can build statistically significant so that you can talk about, certain confidence level that, yes, we have seen either the graviton or some effects of quantumness or quantum aspects of gravity in a laboratory. So you want to do the experiment in a controlled environment. Now let's go back into the history a little bit, because this is such an old topic, especially coming from the quantum mechanical side. In the days of Einstein, Podolsky, and Rosen, the famous EPR paradox we all know, where one of the basic assumptions is the fact that, like classical mechanics, even quantum mechanics should also have a local reality. The concept of local realism was invoked at the time, way back in 1930s, due to these gentlemen. And simultaneously in the same year, you see 1935, when the paper of Rosen, Einstein, and Podolsky came in March, and in the month of August, there was a paper by Schrödinger himself, and this is perhaps to my knowledge at least, for the first time, he actually invoked the word called entanglement, and he says very clearly, which is marked in yellow, that entanglement is something which a classical world cannot mimic. So something, he gave us some idea, essentially at the time, maybe perhaps it was an idea, but it was a very concrete idea, and where he could discriminate between a classical system versus a quantum system. And it took way back in 60s, it took around another 20, 25 years when John Bell came up with his hypothesis, well, not the hypothesis, with the formulation of the problem, where he actually challenged this local reality assumption of EPR. And he said that no, in quantum mechanics, it cannot be correct. And then from 1960s, mid-60s to mid-80s, it took another 20 years to perhaps do an experiment which won the Nobel Prize due to Alan Aspect and many other colleagues. So that's a kind of like a timeline for the quantum mechanics. And when it comes to doing something similar for gravity, perhaps it will take even longer. But again, going back to the history, way back in 1957, there was a Chapel Hill conference where Feynman was very, outspoken about this possibility of testing. Perhaps he was already thinking, being Feynman, he was already thinking how to test quantum aspects of gravity in a laboratory. And he already spoke about way back in 1957 that what happens if you try to bring two masses sufficiently close to each other and try to see the effect due to one mass due to the other mass. So Feynman actually made quite a lot of at the time. He made quite a lot of statements, which turned out to be very, very useful even now, and even for testing quantum aspects of gravity. But one thing which perhaps he was missing at the time, but Feynman being Feynman, perhaps he knew it. He didn't spell it out all in the 1957 famous Chapel Hill workshop. He actually mentioned about building the correlations, but what kind of correlations you would build up, that he perhaps did not spell it out so clearly. So that whenever we want to do an experiment, even in LHC, you have to ask the question, what exactly you are going to observe? how are you going to infer the data from that observation and go back to rule out certain physics or rule in some physics? So some of those things, perhaps, Feynman might have had thought about it, but didn't spell it out very clearly in way back in 57. So these are the theoretical aspects, but even from the experimental side, people have been trying to understand. And one experiment which goes back in 1970, which is very important to mention, is the Colella-Overhauser-Werner experiment. They took the Mach-Zehnder interferometer and they took the cold neutron and they did the interference. They saw the interference in an Earth's gravitational potential. And then way back in 1980s or late 1980s and early 1990s and 2000, there were many experiments being done in where people have taken the cold neutron and they have bounced the cold neutron. They have seen the energy levels of the cold neutron in an Earth's gravitational potential. So it's something similar to like taking a fixed potential, quantizing the particle in a fixed potential. So it doesn't really test the quantum aspects of gravity, but it definitely observes the phase due to gravitational potential, Earth's gravitational potential. And what enters in the phase is, of course, Newton's constant G, and the h bar is the Planck's constant. So you may wonder, G is very, very tiny, h bar is very tiny. Still, we can measure experimentally these phases, partly because the reason is that we are measuring the ratio between G and h, both being very tiny. But if you fix the parameters, the mass, the length scale, and other parameters in such a way that you can see such a tiny phase induced due to gravity. So although gravity is weak, maybe you will not be able to see other effects other than attraction and of two masses, but you could also be sensitive to this quantum phase. So there are other experiments, Page and Gilker. I will not get into that because maybe you can ask me later on about this. There are issues with the experiment, so I will not get into that, but maybe you can definitely engage with me later on. So let me come back to the point that what are the key ingredients when you say that you want to test quantum nature of gravity? What are the key ingredients you want to test, which is different from a classical physics, which is different from the classical world? One of the things which classical world will never mimic is the quantum superposition with Schrödinger cat. The cat is dead and alive simultaneously, can never be mimicked in a classical world. Schrödinger already pointed out to us that entanglement. So you can, so entanglement is like building correlation, but it's a quantum correlation, which cannot be mimicked by a classical world. And the third ingredient, which has been there in a quantum information side, I think more than in, say, quantum field theory or other branches of theoretical physics, since 1980s, this concept they have developed, which is very interesting theorem, is called LOCC. What it means, or what it tells you, that a classical communication between two quantum systems cannot lead to any entanglement. So the last point is also related to the fact that there is an quantum entanglement. And we'll discuss all these three points a little bit more carefully as we progress in the talk. So let's see what's happened with the macroscopic quantum superposition. Now, if you believe that gravity is explained by Einstein's theory of gravity, where you have a metric one side, the geometry, the concept of geometry, and the concept of energy momentum tensor. So the matter sector on your right-hand side. If you can localize the matter, let's say, and if you say that gravity, the curvature responds to that matter, then curvature should also be localized. So imagine if you have a situation where your cat is dead and alive, you will have a curvature at the close to in the localization where the cat is dead as well as the cat is alive. But the question is how massive superposition you have created in a laboratory. So one thing becomes clear. I mean, you can again ask me this question about how do you really test this kind of like hypothesis. So for this, you would need definitely you need to go to a regime where the mass of the system is less than your Planck mass, and the Planck mass is roughly 10⁻⁵ grams. So you're talking about a very, very tiny system. Heavier the system is, it gets more and more interaction, the surface area increases, effectively the system, even if it's quantum, it decoheres. So you need a very, very tiny mass where you can isolate. Of course, you need to still worry upon the decoherence rates and things like that. This is one of the biggest challenge, actually. So the world record is due to Marcus Arndt's lab in University of Vienna, where they have taken 10⁻21 kilogram system and they have created a superposition. And now people have, and that happened way back in 2000, people can create superposition with the atoms, and that can live for a very long time, beyond even second. The coherence time scale for this could be seconds. The superposition length scale could be even meters. So the frontier of creating macroscopic superposition is increasing. It's becoming better and better. And what we would like to see, you would like to see even heavier system, like 10⁻17 gram system, 10⁻15, 10⁻14 gram systems can be kept in a macroscopic superposition. So this is what you would like to see, perhaps in a laboratory. But the technology is so that it's all about technology. It's taking time, but one day it's going to happen soon. The second thing, which I mentioned quite a lot, is quantum entanglement. And as many of you already know about this subject, just a very brief prelude to the subject is that in quantum mechanics, when we teach quantum mechanics to our undergrad student, we talk about pure state, mixed state, and entangled state. We categorize all these states. And simple way to understand this is that if the states are separable, then they are like a pure state, but the mixed state can be entangled. So I mean, mixed state is something which appears also in statistical mechanics, and entanglement is a property where you cannot separate the two states. The states become inseparable. Very simple example is that many times we talk about particle creation from the vacuum. Think about Schwinger pair production. I disturb the vacuum. I maybe by a time-dependent electric field or magnetic field, so I can create pair of particles, it's electron and positron, and the wave function of electron and positron is such that I cannot talk about just the wave function of the electron or the wave function of the positron. I have to talk about both electron and positron simultaneously. That's an entangled state. And that's a very simple example of an entangled state, or the famous EPR paradox appeared essentially from this simple observation made by Schwinger. So, and there are many ways you can quantify entanglement, and I'll talk about that. One is the entanglement entropy. So in a very simple system, like let's take a bipatrial system where your system A and system B, you can trace out the reduced density matrix. You can trace out say either A or B, and you can construct the von Neumann's entanglement entropy. And as I said, that for a pure state, of course, this entropy goes to 0. But for a mixed state, which is like a thermodynamical system, your entropy will not be 0. And entanglement is one of the features of this, that when the von Neumann entanglement entropy is finite, it's non-zero. And what it says that it builds up that there is a correlation, quantum correlation between your systems, between your subsystems A and B. So entanglement tries to show this correlation, essentially, the quantum correlation, not the classical correlation. Classical correlation will be something like you take a coin, which is a classical system, you toss the coin 50% up and down, heads and tails. That's the classical correlation. But a quantum correlation will be different from this 50-50. It will try to give you something different from 50-50. So that's the difference between a quantum correlation compared to a pure classical correlation. So, but when it comes to experiment, you would like to see some yes and no answer. And for that, entanglement entropy is not so good because you have to measure through all the bases, because entanglement is a basis independent quantity. But witness, when you witness, and so when you talk about the observable, it is a basis dependent. And when you perform an experiment, you cannot look into all possible bases. Sometimes you look for very selective bases because, of course, the experiment takes certain time. You want to save some time. So that's why the experimentalists like to work with the entanglement witness, like Bell's inequality or the Bell's witness. So in our first paper, we wrote down the Bell's witness with respect to this Pauli matrix. So essentially building correlation with the say XZ, YZ, so different cross correlations. You look into cross correlation and then you create a witness. So in the case of Bell's witness, this W has to be greater than 1 to see whether the system is quantum or not. So one way to understand is that your entangled state lives one half of this Venn diagram, which I've shown you. So one half you have a separable state, which is like a pure state. The other side, you have entangled state. And the witness is the kind of like dividing line. So depending on the witness, whether it's positive, some witness can be positive, greater than 1 or less than 1 or less than 0. So there are many witnesses you can construct. And as I said, a witness is a basis dependent. So it depends on the choice of the basis you construct, you make. And after our paper, many other people constructed different bases, different witnesses. And one of the witnesses, which seems to be quite popular right now, as far as the experiment is concerned, is the second witness, which is written in the red. So you have identity matrix and then correlation with sigma X, sigma Y's, and sigma Z's. Beside the witness, sometimes for a bipatriot system, it is not true for all systems, but for bipatriot system, sometimes it's also very interesting to look into concurrence. So concurrence, the way you define concurrence is that you take the reduced density matrix again, and then so that definition of concurrence, as I've written down, you take which is defined as C, and it's constructed essentially by the reduced density matrix. If this concurrence C is essentially 0, if it is 0, then essentially there is no entanglement, and the maximal entanglement happens when C becomes √2. And this is due to Hill and Wouters. So the people have been in quantum information side, people have been using many of these ways of witnessing the entanglement, how entangled the state is essentially. So now let's come to the last point, which is very interesting in my opinion. And you will see that although there's sometimes 2 or 3 subjects, they evolve separately, but you will see immediately there is a very interesting link between these subjects. And this is something very interesting to see from an S matrix perspective as well. Although when in the quantum information side, people were not thinking from the S matrix, but at the end of the day, some of these topics are very closely linked to each other. So, so Bennett and his companies, as you know, Bennett is one of the father figure for quantum computing. So way back in 80s, Bennett and also there are many collaborators involved, and there are many people have now written papers in this. So just to summarize, imagine that you are sitting in Ankara and I'm sitting here in say Groningen, and you have a quantum experiment and I have a quantum experiment. We both have quantum experiments, but we are both communicating to each other through a classical line. So there's a classical communication. So I established a classical communication with you. So whatever outcome I get, I can always inform you classically that, hey, look, this is what the outcome I got. Suppose it's a spin up and down. I can say that, look, this time I've seen spin up, and I can communicate that to you, and you can communicate that to me. But this communication, if it happens through classically, then I will not be able to entangle my quantum system with yours. This is what the LOCC tells us. So LOCC, LO stands for local operation. So locally, I'm doing all the operations here. It's a unitary operation because I'm dealing with a quantum system. My Hamiltonian is well-defined. Everything is well-defined. At my end, the same thing is happening at your end, but the channel of communication is classical. So as long as the channel of communication is classical, what the theorem says that I will not be able to entangle you, or you will not be able to entangle my state. The states will remain be separable if they began separable. If they began with separable states. Now, if they are entangled, suppose you can also create a system that we have entangled states between, we have already created an entanglement. But then after the experiment, after this classical communication, I will not be able to increase your entanglement, or you will not be able to increase my entanglement. So degree of entanglement will not change. So that's what this is, this talks about. So the question is, how do you really create this entanglement? So the only way which you can create this entanglement is you revert this classical communication to a quantum communication. Now, if we do the same experiment, sitting in Groningen, I do an experiment, you do sit in an experiment in Ankara, but now if we communicate, if we interact via a quantum channel, then I will be able to entangle with yours and you will be able to entangle with me. And if you think from a particle picture point of view or field theory perspective, so you can think about creating an S matrix. Very far away, you can think about Alice and Bob. But now, if the Alice and Bob, they don't interact if there is an interaction, but let's say that this interaction is classical, then Alice and Bob will never entangle in the final state. However, if this entanglement happens via quantum channel or quantum interaction, and that we know at the tree level, at least it will happen via some propagator, Feynman propagator, then the final state of Alice and Bob will now get entangled. So that's the a very simple way of understanding the QC part, the quantum communication. So now the quantum communication is nothing but the quantum interaction. So even at this tree level, you have this already embedded in any particle theory. Like take an example of Coulomb interaction. It's happening via photon, or Casimir interaction. It's happening via dipole-dipole interaction. So there are two photon lines. So they are interacting. And we know that photon is quantum. So in any of the QED experiments, my final states are entangled. And the same thing is happening with any gluon exchange or QCD or any standard model interaction which we are talking about. Or via Higgs, we know the Higgs bosons is also quantum. So any Higgs exchange will lead to final states, entangled state. But in the case of gravity, this is the question. Is graviton really classical or quantum? And this is the place where we can potentially test the nature of gravity. So let's go a little bit forward, and this is a paper which will appear soon. So let's construct it just to illustrate this point. It's a pedagogical paper. It's nothing fundamental, very simple, very pedagogical. But sometimes the pedagogical papers are also very nice because it tells us a little bit more about the nature of physics as well. So let's take two simple states, two harmonic oscillators, nothing beyond that, two harmonic oscillators. And let's say these harmonic oscillators are interacting with, say, graviton. So that they only see interaction is via graviton. So initially, let's say that they are sitting in a ground state. I can construct the ground state. And if I introduce some interaction, HAB is my interaction, which I'm assuming it to be happening via graviton, then what will happen is that in a quantum perturbation, very old perturbation theory, not even the new way of doing perturbation, just the classical mechanics, quantum mechanics, the first quantum mechanics which we teach our undergrad students, we do the perturbation theories, exactly the same perturbation theory. So the initial state, let's say that they are sitting in a ground state, because once I switch on the perturbation, it will evolve. And the wave function will evolve, it will become the final wave function, which you can compute. And you can see immediately that, initially you started with the ground state. After the interaction, this harmonic oscillator will get into excited state, maybe with a different occupation number, say N1 and N2. But once it gets evolved in the perturbation theory, if you look into the wave function, you see that there's a very interesting combination, which I have shown here in my right-hand side. You can see the last term, the yellow shaded region, actually shows that now the states are such that they are mixed, they're entangled, they're no longer separable. So it's very simple way of seeing this even in quantum mechanics. So undergraduate level quantum mechanics I'm talking about. So now let's talk about how do this two harmonic oscillator will exchange graviton. One way you can think about, okay, there is an off-shell exchange. There's a virtual excitation of graviton, through which it can interact. Now, if you assume that, okay, these harmonic oscillators have some intrinsic motion, then they can also interact via gravitational wave, on-shell exchange of a graviton. So you can have both the possibilities. And as a consequence, you can do the calculation for both the cases separately. So there are two ways of entangling masses via quantum nature of gravity. In the case of off-shell exchange of graviton, is the spin 2 and spin 0, both the components contribute. That we all know from the days of Sujan Gupta and Bleuler, Gupta-Bleuler formalism, as well as Kibble, Feynman. Many people have computed these calculations. So I'm not inventing new tools. I'm just using their tools to do the calculation. So essentially, you are quantizing the spin 2 component and the spin 0 component, and then compute how the and you take energy momentum tensor. So this is the off-shell part on one hand, and the on-shell part, you know the energy momentum tensor of the two harmonic oscillators. You give a gentle motion with respect to each other. So there is a relative motion between the two harmonic oscillators. You are quantizing the Hij component, since the transverse and traceless component of the graviton, which you are quantizing here. And here on the off-shell case, you are quantizing spin 2 and spin 0 components. So these are the things which you are quantizing. And you know the interaction. This is the universal interaction of graviton with respect to your matter, which is given by a h mu nu t mu nu. And keep in mind, everything I'm doing it in a perturbative quantum gravity, nothing fancy, no non-perturbative aspects of quantum gravity. And if you want, you can do that. And some people are already doing it, this kind of calculation in loop quantum gravity, in the context of loop quantum gravity. But anyway, sticking to very simple basic questions. So you can compute, in a perturbation theory, you can compute what happens to the first order correction to the potential, essentially looking into the eigenvalue problem, and second order correction to the potential, to the change in the energy. And so happens that the first order correction vanishes because your operators P and P dagger, they act in your vacuum. And this vacuum is a graviton vacuum. So you want to understand, because you kept the mass, and you want to see how the graviton vacuum is changing now. So you're doing the perturbation theory on the graviton vacuum. And you can compute the gravitational change in the gravitational vacuum, but that will come in the second order in the perturbation theory. So K is your one particle state, essentially. So one graviton state here, which is given in the off-shell exchange, is given by the spin 2 component and the spin 0 component, P00 and P, because I'm taking the static limit, in the static limit. And yeah.
So here you're omitting the graviton self interactions, right? Just at theory level.
At this point, I'm ignoring the graviton self interaction, but you can consider it. You can also take into account of one graviton loop, and you can do the calculation. It will be a little bit more hectic calculation, but you can do it. Nothing stops. So let's assume that these two masses are sitting static in its potential. Their separation is d. And they have a width, because after all, this is a Gaussian wave packet for the harmonic oscillator. So they have a width delta XA and delta XB for the two systems. Okay. Now you can compute the potential. It's nothing, but there's no surprise. The potential is Newton's potential. But now the important thing to notice is that your XA and XB are not numbers, but they are operator valued quantities. XA and XB are operator valued quantities. And you know the position of the two harmonic oscillators. So you can expand them along the, the modes, the annihilation and the creation, and the A and A dagger, and similarly for B and B dagger, you can expand them, and you can construct at the lowest level in the Newton's constant, you can construct the Hamiltonian operator, which is now just contains only the A and B's, the mixing between A and B's. So what happened is that you have, by computing this gravitational energy, changing the gravitational energy, what you have done is that you have integrated out all the graviton degrees of freedom, and you're left with purely the matter-matter interactions directly. And it looks like a contact interaction, nothing very fancy here. And with this Hamiltonian, you can now compute the evolution of the wave function, and you see that the evolution of the wave function at the lowest order, the ground state and the first excited state, because you are just doing the one graviton exchange problem here, you see that now the concurrence is non-zero. So it means the system is getting entangled. And this is what the LOQC comes in. LOQC comes in the fact that your HAB, the Hamiltonian which you have got, is a quantum Hamiltonian. And you can compute the entanglement phase, very similar to, it's nothing but a very simple way to understand. And a phase is nothing but action divided by h bar. Action is given by your two static masses, which is Newton's gravitational potential. There's no kinetic energy. So kinetic potential energy divided by h bar will give you the phase and the time it takes to do this entire procedure. Maybe the time. Here, the time will be related to the coherence of the time harmonic oscillators, how long these harmonic oscillators remain coherent. So essentially, you can compute the phase as well. You can repeat the same calculation for the gravitational waves. I will not go too much into the details, but you can ask me later on. In the case of gravitational wave, instead of going to one excited state, you go to the two excited states. Again, it's just, if you're doing quantum field theory, you will see immediately, because it's a matter-matter graviton. Actually, if you want to really do this problem, the graviton emission, you would require, from the energy conservation, the state which you excite is the second excited state which you will excite. And again, this comes essentially from the interaction. You see that it comes because you have A dagger square, B dagger square. These two term combination will give you the second excited state. You can compute again the concurrence, and you see again it's a positive that shows that even if you treat gravitational waves, it's a quantum. If you treat it quantum mechanically, then it will entangle the two harmonic oscillators. So very simple calculation, but very interesting. Okay. And I think from quantum field theory approach, we know that there's nothing but at the end of the day, you can construct a Feynman diagram, and you can talk about S matrix. And you can not only restrict yourself to tree-level exchange, but you can go for higher order corrections, 1 loop, 2 loop, 3 loop, and the story will be the same. You will always get the final states to be entangled. So what is the protocol? So having laying down the entire theory aspect, you can ask how you're going to perform this experiment. So the way you're going to perform the experiment is that now, as I've shown you the harmonic oscillator problem, but what you can do in a laboratory, you can create localized masses, localized states. And that, as I said, that Arndt's group had done this experiment. So you can try to create a Schrodinger cat state. And the way you create Schrodinger cat state through a Stern-Gerlach apparatus. And if you remember, the Stern-Gerlach apparatus is actually an acceleration mechanism. You create an inhomogeneous electric field, or the magnetic field, inhomogeneous magnetic field. You throw your electron, the spin up and spin down, they get separated. And this is the acceleration mechanism, essentially. So essentially with this mechanism, but now instead of doing with the electron, you're doing it with a very heavy system, because you want to essentially be sensitive to this mass. That you need a large mass. So question you can ask, how heavy the mass of these Schrodinger cat states should be. So you create two systems. So one Stern-Gerlach apparatus on your left, then another Stern-Gerlach apparatus on your right. It's Alice and Bob. So they're separated by a separation distance of d, and they're exchanging some virtual gravitons. And let's say that the coherence time scale is tau. So as I said that as I showed you the case of harmonic oscillators, you can compute the entanglement phase. And that entanglement phase is given by the combination of left-right, right-left, right-right, and left-left. So all the phases accumulate, and you can compute the entanglement phase. And the entanglement phase is given by this quantity, which is 1 over d minus delta x, 1 over d plus delta x minus 2 over d. And then you can also create a witness. As I showed you in the very beginning, what is important is not to measure the phase, but to see whether the witness is positive or negative. And so you construct the witness with the help of this sigma matrices. And after doing the experiment, if you find witnesses in this particular base, if it is negative, trace of W rho is negative less than 0, then only you can say that graviton exchange is a quantum entity. So there is a yes, no. If it turns out that after a billion times doing the experiment, billion times repeating the experiment, you find statistically it is not, then it's not. But if it is, then it is. So you create a witness which is very, very sharp. But in order to do this experiment, you really need to pump up your mass. The mass has to be 10 to minus 14 kilogram. So it has to be quite heavy. So almost 6 or 7 orders of magnitude from what people have done now to what we need to achieve. The separation delta x, the macroscopic superposition which we are talking about, has to be roughly of the order of 10 to minus 4 meter. And the separation, the closest separation, roughly around 200 micron meter. And you have to keep this system coherent for roughly 1 second. So extremely massive object, 10 to minus 14 kilogram, you have to keep it for roughly 1 second. And it's extremely, extremely hard challenge, experimental challenge. So, and then only you can measure the phase, which is roughly order 1. The larger the phase, better it is, because the system has more time to entangle. So you can create your witness. You can, by repeating the experiment many, many times, you can say whether, graviton here is really a classical or a quantum entity. So what are the experimental challenges? So for the remaining time, let me go back to the experiment, because the experiment you will find is much more interesting, and it's kind of things which it involves. It really blows up our mind, because we need expertise from LHC to quantum computing to all the branches of quantum system has to come in together to create this experiment. So one of the things I have been telling you, that one of the biggest challenge in quantum mechanics is the decoherence, because you keep a system, it interacts, it's a scattering process in any normal quantum mechanics and in quantum field theory. As it scatters, it decoheres the system. So, but in order to perform this experiment, you really need to keep the system coherent, and for a long time, for a very heavy system, for a long time. So you need to take into account of the decoherence effects. So there are many ways you can create the decoherence, or many ways you can lose the coherence of your system. Essentially, atmospheric, the molecules, the particles, you can, the system, if it gets heated, it will lose the black body radiation, or the photon, if you impinge upon it, it will lose the coherence. If there is a cosmic ray, if it hits the if the system is hit by cosmic ray, it will destroy the coherence. If it is hit by, say, neutrino, it will, or axion, or you name any interaction within the standard model, beyond the standard model, it can destroy the coherence. So it's one of the hardest thing to manage. How would you keep the coherence of the system? So I'm not going to go through the maths, it's not so interesting, but let me go through the physical situation, how you're going to do the experiment. So the way people now are thinking about doing this experiment is to take diamond. Why diamond? Because diamond is quite dense, but not only it is dense, but when you go and buy a diamond in any jewelry shop, you find the diamonds are never very pure. Naturally occurring diamonds always have defect. And that defect is because there is some bond which is not carbon 12. It can have carbon 14, or it can have some nitrogen. So nearby, if you look into the periodic table of carbon, there are nearby elements, and naturally occurring diamond will always have some impurities. So one of the very common impurity which you find is the nitrogen valence. So there is a bond missing, and it has a nitrogen, but there is an element which is missing. When one of the electrons missing, that gives you nitrogen valence. So nitrogen valence is called NV. So the diamonds, naturally occurring diamonds, have this nitrogen valence. Many of these diamonds have nitrogen valence defect. And nowadays in experiment in laboratory, you can find it out where the defect is localized, even in the diamond. So let's say that you have figured it out experimentally, and this is a routine job now in a laboratory. You know the Hamiltonian of the system. So what happens in this nitrogen valence, our experimentalist colleagues can dope an electron. So you put an electron inside this. So this system becomes a heavy atom with an electron. Imagine heavy hydrogen atom. It's a huge mass because it's very dense. One electron, and that's your system. So it becomes your electronic system. It becomes, you can now manipulate the state of the system. You can have spin up and spin down depending on the magnetic field where you keep it. In an inhomogeneous magnetic field, you can keep this diamond, very massive diamond, with a spin up and down, and behaves like your any spin system, because it can interact very electromagnetically. All the electromagnetic interaction is susceptible to. But not only that, so this is the last term, the NV colored part in the Hamiltonian. The second part is the diamagnetic part, because again, so if you put this system in an external magnetic field, it will create a self-interaction, and self-energy will give you this diamagnetic part, which is proportional to the magnetic susceptibility of the system. And the second and the third from the last term is it's almost like a cosmological constant. It doesn't affect your spin system. It's like a zero field splitting. So the last two terms in your Hamiltonian are the most important. And the mass is the system, and the momentum is the, this particle's momentum. So now with the help of this Hamiltonian, so you know the Hamiltonian, you know the intrinsic property of your diamond, you try to create a macroscopic superposition in an inhomogeneous magnetic field. But keep in mind the kind of masses which we need, no one has gone so far. So we are now trying to come up with an experiment, the configuration in our lab, in our group, as well as in other groups in the world, where they're trying to think about how to create this macroscopic superposition. But before even going towards this creation, there are enormous challenges. The challenges are, right now, actually, I have become more and more experimentalist rather than theorist, because I'm trying to compute all these uncertainties, all these challenges. How do you create an initial wave packet? How do you neutralize? Because you have created an electromagnetic system now. But you want to, at the end of the day, when you want to measure the gravity effect, you want to suppress the electromagnetic interaction, because even electromagnetic interaction will entangle the system. So you need to neutralize the electromagnetic charges. You need to cool the diamond, because the diamond inside there are phonon vibration. You want to cool it down sufficiently that even the phonon vibrations cannot destroy the coherence of the system. So you need to go all the way to roughly 1 Kelvin temperature. You have to cool down the system to roughly 1 Kelvin internally, below 1 Kelvin, so that the phonon vibrations are they are suppressed. They are not destroying the coherence of the system. There are external cooling. You need to put the entire system in a vacuum, which is as good as the vacuum in the LHC. So Gabriel said, there's a guy from Northwestern. He's quite senior physicist, and he was he's a kind of father figure for creating the vacuum in the LHC, where exactly the proton-proton beam are colliding. And that place is extremely highly, very excellent vacuum, one of the best vacuum which we can create on Earth, where if you look into the vacuum there, it's roughly 10⁻⁻15, 10⁻⁻16 Pascal. Not even a molecule is sitting there. You suck up everything. So that's the kind of vacuum you want to create here, because even a particle, even a single particle can hit the diamond and destroy the coherence of the system. So there are many, many challenges. You have to externally cool the system. You have to create one of the best vacuum. There are other instability problems, because if all these things you are creating through inhomogeneous magnetic field, you are creating through current fluctuation will lead to decoherence. All the things, you name it, and you will create decoherence for the system. So it has to be extremely, extremely sensitive experiment, perhaps one of the world's most sensitive experiment you can ever imagine to perform. So that's why it's so hard to perform this experiment. So, so right now, as far as the standard model interactions are concerned, you can compute the decoherence rate, because you do not know from the beyond the standard model physics, because they can also interfere and can cause your decoherence. So that's another problem. But at least for the known part, you can compute the decoherence rate, scattering rate, and you can see the black body radiation, the interaction between air molecule, or you can shield it. You have to have a very good shielding so that you're not sensitive to your cosmic rays events or neutrino events or even axion or dark matter hitting the system. So one of the interesting things is the Casimir dipole-dipole interaction. Even Casimir force or Casimir interaction will also entangle the system. And when you bring in the two systems fairly close, around micrometer, this creates the largest background, the largest known background. Of course, there are unknown unknowns, but this is the known background which you know. So you have to make sure that you overcome this background. So at least you want this background to be suppressed compared to gravity. The gravity-induced phase should be at least 10 times bigger than the Casimir dipole-dipole interaction. So this is something which you need to make sure. So you need to avoid any surface defect. The diamond which you're talking about has to be fairly smooth. You cannot have any surface. The electromagnetic interactions you can actually ameliorate by creating a Faraday cage inside and outside. So some of these things which we are investigating to mitigate the patch potentials, mitigate the Casimir potential. But gravity, whenever you want to do an experiment with gravity, gravity itself becomes its own enemy, because you want to create a system which is freely falling. Because so the whole idea is that you are creating this Stern-Gerlach apparatus which are freely falling in Earth's gravitational potential. So there is no, inside the capsule, there is no acceleration, no gravity-induced acceleration. But there could also always be jitters. Suppose a butterfly passes by, or if a plane passes by, or a TGV train passes by, it will create a jitter. And that will give you a relative acceleration, gravity gradient noise, because even the capsule, the box, is just the equivalence principle. You cannot go to extremely small apparatus. You have to have some capsule which is finite length. Even that finite length, finite box gives you a noise effect, the gravity gradient noise. So you need to take into account of all these things. And these are the noises even LIGO takes into account, even the Einstein telescope, which they are building now, they also have to take into account. Even in LISA, you need to take into account of all these noises, but in LISA it's a different story because some of these noises are better managed. But nevertheless, one of the offshoot of this experiment is that you are creating one of the best sensors, quantum sensors, which can measure acceleration, which is 10⁻⁻15 to 10⁻⁻17 meter per second square within 1 second. So anyway, so here you can see on the plot there are seismic noise, there are continuous motion, the jerks, the planes passing by, trains passing by, they will all create some jitters in your experiment. So you need to somehow mitigate that. You need to take into account of all these kind of noises for the experiment. So one of the best design we can conceive right now is to go underground and have a drop tower. So underground drop tower, because underground the seismic noise is very low. That's why LIGO, all the gravitational wave experiments, they go underground. So that's one of the biggest advantage. But not only that, you have to have a kind of like a Russian doll configuration, where you have the innermost capsule where you're performing the experiment, and now they are being shielded by various levels. So there are many, many levels you have to bring in, because you want to protect it from various acceleration, this relative acceleration noise or gravity gradient noise. And the innermost capsule is the one where you do the experiment, has a pressure which is 10 to minus 15, minus 16 Pascal, maybe outside that, slightly less pressure, less demanding pressure, and so on and so forth. And you let it free fall. And you do this experiment, you need to do the experiment a million times, billion times to build enough statistics, because it's a matter of statistics at the end of the day. That's why you cannot go into the space. You have to do it on Earth. So we are already trying to build some of these experiments, creating this Schrödinger cat state in a laboratory. I'll not go into the details. If you are interested, I can tell you what we have achieved so far in the laboratory. You can probe various aspects of gravity, not only just Einstein gravity. As I said, you can test various different forms of gravity. You can see maybe new physics coming up, local gravity, non-local gravity. You can test perhaps wild curvature gravity. Of course, it will be becoming hard. It will not be so easy because there are unknown parameters, but maybe you can constrain those parameters. Maybe you can test Yukawa nature of gravity as well as short distances. As I said, that you can come up with various designs. Now you can think about interferometric design where you have parallel setup, perpendicular setup, or star-shaped setup. So now various different groups are also exploring this kind of possibility, that what kind of setup should you have, or maybe some array. Maybe there are many such arrays you build up, and then you look into which one gives you better witness. What is the number of measurements you need to do to get enough confidence level? So many groups are trying to do this, and I'm just showing you from my group, but there are other groups who are playing similar kind of games right now to know that how much confidence level you can build up in these experiments. And you can see just the bulk part of it is that you really have to repeat the experiment many number of times to do gain the statistics. Now, even if you say that this experiment takes 1 second, if you have to do the experiment for 10,000 times or repetition, it will take at least a year to gain enough statistics, or it can go even more. So there are many challenges. But having said so, I mean, there are many physics which comes together. As I said, the cooling, refrigeration techniques, you are testing foundations of quantum mechanics, quantum foundations of quantum field theory. You are testing even beyond the standard model physics as well to some degree. There are atomic trapping, levitation techniques, condensed matter system, because you want to understand maybe today we are talking in terms of diamond, but tomorrow maybe a new material may come up, may help us in designing this experiment. Not only that, we are trying to understand Casimir patch potentials, very low energy QED. You can do a very low energy QED with these kind of experiments, the decoherence rates, and all sorts of things. There are many things which can come together to unite all these aspects. There are also, you can discuss about non-perturbative aspects of gravity, and many people have done that. Rovelli has been working on it quite a lot. Because so far I have discussed, I'm assuming that there's a S matrix formulation of field theory exists, but there are versions of quantum gravity where the S matrix formulation is not there. So how you are going to test some of those hypotheses with these kind of experiments, but I will leave it for future discussions, or maybe after the talk we can discuss. So just to conclude, because my time is running out, I think it's a very interesting way to test quantum nature of gravity, because this is something we need. Our community needs an experiment. Like as I was given you an example, the kind of LSC has done to our community in the particle physics community, we need something similar for gravity, because otherwise without experiment, whatever we say is the string theory, loop quantum gravity, these are very nice mathematical ideas, but at least you need to test it at some level. And perhaps perturbative quantum gravity is the simplest way to, you have to put your first foot forward. Perhaps this is the simplest and best foot forward right now with the current technology. So with this, let me thank all of you for listening, and I'm happy to take questions and discussions. So thanks a lot for your patience.
Yeah, Anupam, thanks a lot for such a beautiful talk. So I think you have time to receive a couple of questions or comments. Yeah. So is there any question, comments? Yeah.
Excuse me, I have a question.
Yeah.
Sir, in experimental setups, how do scientists know that two systems, the entanglement has destroyed? How do they know that?
So what they will do is that they will look into witness. So it's good question, very good question. So they will look into this witness. Say for instance, so you see that system 1 and system 2. So system 1, you have finished the experiment. You see that you measure the spin directions. But very simple way of understanding will be that you measure how many times you got spin up and how many times you got spin down. So maybe if it's purely a classical correlation, you will get 50-50, 50% spin up, 50% spin down. But if it's a quantum correlation, you will find that it's no longer 50-50, but maybe 51-49 or 50 point something and 49 point something. So this is the way you try to build. So for experimentalist perspective, what is important is to understand this witness, is to construct their witness, not only construct, but to read the witness. So that's the most important thing.
So another thing, means what is classical communication? The theorem that you, that statement that you gave, that classical communication cannot create entanglement. So how do we categorize classical communication? Means all the things are through electromagnetic waves.
Yeah, I mean, suppose let's say that someone doesn't believe in quantum gravity. I mean, you know, you need to go from that point of view. Someone says that no, I just believe in classical gravity. So classical gravity, some simplest example will be the two players playing football. Like for football, passing the football is a classical exchange. I can always think about you know, doing the experiment in Groningen, and I can tell maybe you, wherever you are sitting there, let's say classically through, you know, Dove is sending my message to you. That will be a classical interaction, for instance.
Yes. Thanks.
Yeah. Is there any other question, comment?
I have a question, but
Good. Go ahead.
What if we have some space-like separation between this harmonic oscillator? I mean, I know you want to calculate the quantum the entanglement via this gravitational interaction, but and as you indicated the previous page, you said that you cannot get the information out of the light cone. But as we know, the gravity can. Recently, there are some comments about this information paradox. As you know, they said the radiation, Hawking radiation, is somehow entangled with interior of the black hole. So in this case, there's some kind of out of the light cone perspective. So my question is, what if we have some kind of space-like separation between these two interacting harmonic oscillator systems?
Yes, and it's a very interesting question. So the point is that, first of all, those who talk about this, they have to answer the basic question: what is the mechanism? I mean, from perturbative quantum field theory, we know at least whatever we have learned from LSC and whatever you know, any experiment we have dealt with, we have always done with the presumption that causality is maintained. Once I give up on the causality, then how would I really do the experiment, or what is the formulation? That itself becomes questionable. So maybe one should ask those people, those who talk about this black hole information loss paradox via non-local or you know, the causal, non-causal, you know, dynamics. One should ask what exactly is the framework. So I don't think in a perturbative sense we can talk about, but there could be some non-perturbative sense, and your question is very nice, and one should explore this possibility. But so far, I mean, since so you need to build first a mathematical setup, and then maybe we can ask the question, given that mathematical setup, how to perform the experiment and what would be the observables and things like that. Yeah, but the question is valid, and you can think about it. That you know, how to first conceptualize such a theory, which will have where you give up causality, and once you come up with the theory, of course, then you can perhaps test it also.
Yeah, Any other question, comments?
Can I have a
One more
question?
sir.
Yeah, Kumar, do you have question?
Yes, sir. One more question.
Yeah, go
What
ahead.
is the meaning? What is the meaning of the statement, sir, that curvature is localized? That you mentioned
Okay.
earlier.
So
Curvature is localized.
yeah, so you can think from this even from simple example. When we computed the change, so we were asking the question that how the gravitational vacuum is changed. You see, now the delta H, essentially the change in the gravitational vacuum. Now, when you compute, you see that XA and XB are operator product. So XA is a quantum operator. You see that you can talk about now when XA acts on a vacuum, you can talk about whether it's situated here or here, depending, because we are doing this Schrodinger cat experiment, you see. So in this respect, the gravitational potential energy is not a kind, pure classical quantity, classical number, but it's a quantum valued operator. So it's a very simple way of understanding that how even once you can compute the gravitational potential, the gravitational potential is nothing but the R0101 component, essentially. You can compute the Riemann, essentially, term as well. And you can think from that perspective that now the Riemanns are, particular component of the Riemann are now getting, localized. In a very simple example, when their particles are static. But if they're moving and all, then you can compute various other components of Riemann as well.
Yes, thank you.
Yeah. Any other question, comment?
Can I have a question, Suat?
Yeah.
Anupam, wouldn't it be better to ensure that A and B are quantum objects? So wouldn't it be better to use, for example, Bose-Einstein condensates for A and B? What would you think?
You are absolutely correct. But you see that the diamond is the in some sense, it is a Bose-Einstein condensate. It's a very highly.
Very good.
That's
I see. It's okay. So, but I mean, you have shown us all these experimental difficulties and subtleties. So, I mean, what do you think personally? Is it possible to isolate this spin-2 exchange? Indeed, I mean, is it possible to isolate it from all these remaining interactions?
Yeah, this is what Durmush is a very good question. And this is what we are trying to understand. So we are trying to understand this. And right now, the basic experiment, which is last year we have done with a group in Israel, it's amazing. It's an atom chip. So very tiny atom chip you take, and it creates a magnetic field gradient, like the one which I've shown you with the blue and yellow. This is a magnetic field configuration.
Yes.
Just I've shown in one dimension, but of course there's a two dimension, because on a plane you are creating the magnetic field. And what we could achieve is to create a superposition with this around 10⁻⁻20 kilogram system with the Stern galaxy, so with one loop completed completely. But this is done in a room temperature. Now you really need to cool it down. And we are talking with this stalwart Gabriel Gabriels, who has really helped creating the fantastic vacuum in LHC. So you see, now it's a matter of money. Now, if the agencies are pouring money, if many countries participate, and it will not happen just in one lab, it will be like LHC. If many countries are participating, then we can actually do that. Now, of course, it will take time. But it's exactly like, the childhood dream of Star Trek, Scotty, beam me up. Now the Scotty beaming up is a very tiny, 10⁻⁴ meters. But even to achieve that, it is a huge challenge. But it is possible. It is possible. Now the matter is how much money we want to invest in this game. And of course, the governments would like to see a prototype experiment. Even in room temperature, if we can create 10⁻17 kilogram, this is the we are trying to achieve. Then maybe many agencies will be interested, even CERN will be interested, and the facilities are there. I mean, creating the drop tower, all these facilities, we know we can do it. But now, of course, creating the superposition is the biggest challenge. And also, not only that, bringing two superpositions, because now we can say from particle physics community, okay, besides gravity, you can also have axion, you can have, other interaction, dark matter induced interaction. What happens to those? And if we don't know, these are unknown unknowns. But nevertheless, maybe they give us a possibility. If I'm trying to do the experiment for gravity, maybe I can find out some new particle which can entangle, which will be nice even.
Anupam, also this diamond, depending on the impurity content, it gives off different, you know, radiation, light. I was actually asking it, I mean, are you sure that you have pure diamond cooled down to, you know, I mean,
No,
isn't
no,
it?
very
Yeah,
good question. These are very good question indeed. No, it is not trivial. By
Yeah,
no means it's trivial.
Okay.
By
Mhm.
no means. You really need to know, just to give an example, suppose I take a diamond, but the defect is not at the center. If the defect looks slightly displaced, and I cannot change the location of the defect. So I have to now
Right.
change my configuration. So essentially it becomes like a quantization of a hydrogen atom. You have a quantization of angular momentum. So you have
Right.
spin angular momentum as well as orbital angular momentum because of the displacement. So it generates a torque. So my diamond will no longer be static, but it will start rotating. You see, there
Perfect.
are, you know, I have.
Perfect. That is something I was going to ask. Good. Very good. Yes.
So I have jumped into experimental field, and now, you know, in experiment, I think you immediately realize that you want to solve one problem, immediately there are other problems come and bite you. Life is not easy here, but no.
Thank you.
But
Mhm.
point is, as long as we know all these problems, but these problems, because you can model it, you know the Hamiltonian, you can model it.
Yes.
Three-dimensional modeling, you can do it. That's not a problem. The problem is that, of course, when you do an experiment, and if the diamond may have, so there are some, you know, fluctuations that will be there. I mean, so that's why you need to repeat the experiment. It's not a one experiment which will tell us after a billion times, maybe we will come to know. But I think still it's worth. If you agree with me, if you will see that it's still worth, because even there is no experiment where we can confirm this kind of
Okay.
thing.
Mhm. Thank you much. Thank you.
Any other question, comments?
May I ask something?
Yeah, go ahead.
Can you hear my voice clearly?
Yeah.
Okay. By the way, I kind of missed the first half of the talk, so I'm sorry if you already mentioned this, but I've seen in the literature that there are some criticisms about this experiment, that even in the case of we see an entanglement due to the gravitational attraction only, this is not enough to say that gravitons exist. Can you elaborate on this one? Like,
Yeah, sure. Thanks. Yeah, so there were some, I remember way back in 2017, 18, there were papers by Baylock, Hu, and all the company who were trying to address this point. If I understand their point was that there are, I mean, okay, so this is something which is not, I don't quite agree, but the point is that even they were saying the Newtonian gravitational potential is a gauge artifact. But, you know, we measure gravitational potential even classically. Earth's gravitational potential we measure classically. So it's no longer a gauge artifact. So I think their formulation itself was very, you know, different. So that's one part of the criticism they had. But now I think now they perhaps agreed, because they are not harping on that. There are other people, you see, even for Bell's inequality. So you can even challenge at a much higher, deeper level. Even to Alan Aspect's experiment, there are some loopholes. So there is always an experiment, in quantum experiment, there are loopholes. So the question is, how are you going to make a loophole-free test of gravity? Now, having said this, it is indeed always challenged. You can always find certain loophole where you can say that gravity is not quantum. But I feel that entanglement and witnessing the entanglement is the way to close it down. I think this is the only way I can, because you see that everything which we are using cannot be mimicked by classical physics. Now, having said so, you can still have some non-classical interpretation other than graviton, and it will be nice. I mean, that will definitely make the subject much more vibrant, even at the level of perturbative quantum gravity. So I would welcome if you can come up, if anyone can come up with a different alternative, different way of thinking about the nature of how two particles mediate interaction. I think that will be fantastic. So I don't think it's a criticism. I would say rather you learn something new perhaps from these kind of activities. So I would say, yeah, please let's investigate even those activities which does not require the nature of graviton, maybe.
Okay, thank you.
Any other
Can I ask you a
question?
question?
Yeah.
Let's say we have justified gravitational entanglement. Is there any route from this point to the cosmological constant?
I mean, it's a very good question, but unfortunately, I don't know so much, and I can say my logic behind it, because experiment you are performing at micrometer distances, you see very tiny distances. And cosmological constant is on a very large scales. So maybe there is something deeper, but so far, I mean, I could not relate that what this experiment will teach us about the nature of cosmological constant. So I could not see, but if if you have some ideas, yeah, why not? I mean, it would be very nice. I mean, maybe you can ask,
I cannot see either.
maybe you can ask the question, can I be sensitive to one loop graviton? Because cosmological constant is related to a vacuum. And with the current parameters, it will be hard. But if you stretch yourself, maybe you can create a very tiny superposition and you can do manipulations at various levels. Maybe you will be sensitive to one loop graviton. And that will be very nice. That will be very nice also.
Yeah. Any other question, comments? Anupam, I have a question. Well, not exactly a question. Well, I will remind you the problem, the so-called problem of time in quantum gravity.
Yeah.
So here, graviton is quantized, and we know that the time there is dynamical. So, will there be a problem in the case of measurements?
No, it's a very good question, and I think I would say Carlo Rovelli and even Ashtekar we have been talking about a little bit. So it's a very good question. So here in this, from at least the way I have shown the mathematics here, I have taken quantize the three spatial. But your point is absolutely correct. I mean, how do I know even what happens to the time? Is it an emergent phenomenon?
Exactly.
Or is there something much deeper going on with the time? And so it's a very good question. And actually, this kind of experiment can shed some light. So what's happening is that you are releasing. So suppose here you are, imagine these are my hypersurfaces, like ADM formalism. So these are hypers. Just to, I don't have a board. So just imagine my two hands. I want to evolve things from here to here. Yeah. So this is in the time. So I have created my superposition here.
Okay. So like ADM formalism,
just like ADM form. Just think about it. So I have created a superposition here. Yeah. Now I don't know what exactly is happening in between, because it's a Schrodinger cat state.
Yeah.
And I'm measuring things at much later time. So this is my time. So my time concept of time exists here, and my concept of time exists in this hypersurface. But in between, I really don't know what is exactly also the concept of time. I'm not doing the measurement in between. I'm measuring things I know that I have created. So I have a wristwatch, I have a my ruler, I know exactly that I have created it. But once I've created it, it is up to here. And then I'm observing here.
I see.
Between what is happening, we really don't know. And this is a place, this is a very good question. That can I test some non-perturbative aspects of quantum nature of gravity? Or can I test some aspects of space-time in between what's happening?
Well, if it gives information, it will be, well, amazing.
It will be amazing. So now it's question of, let's suppose you want to say that I want to, if I have a formulation. So something which so far we did the calculation for the perturbative quantum gravity, but now non-perturbative quantum gravity, one step will be to take loop quantum gravity. Now you can ask the question, suppose you don't believe in the graviton, you believe in the creating, take a host action, which is a host Hamiltonian, and you want to create a holonomy. So maybe the holonomy is given by your loop or given by a volume. So if you create a holonomy in between what's happening, because you see that it's a free fall system.
Exactly.
So suppose you don't believe in a perturbative quantum gravity, you believe in purely non-perturbative quantum gravity, you can ask the question, how are they going to entangle? So these are the questions you can definitely formulate, definitely answer, but you need to know the formulation itself, that how do I define what is happening? So in this respect, this kind of experiments are also very nice to provoke these kind of questions, that what is the meaning of time? Does time exist in between or not? But time is of what? Is there not the wristwatch time? It's the time of the Schrodinger cat states. How are they going to keep this track of this time? So maybe you can ask many different questions in this context.
Very good. Thank you. Any other question, comments, suggestion?
May I ask a question? To understand better, to have a clarification in my mind.
Sure.
For the proposed protocol, what gonna be measured is the entanglement witness, right? And then if entanglement witness has a value showing that the two systems are entangled, what we learned is these two systems are interacted with a quantum interaction, basically. But the hope is isolating really well all possible interactions such that only remaining interaction is the quantum interaction due to gravity.
Yeah.
Am I correct?
You're absolutely correct. You're absolutely correct.
And then, what we have at the end is, so in a sense, an indirect observation of the graviton by having that quantum interaction. So we learned that there is graviton, basically. We learned that there is a graviton. Then learning about the graviton, that quantum nature, you mentioned about that Weyl gravity, you cover kind of interaction possibilities. Will it say anything further about quantum gravity? Do you think, what I mean, we learned that there is a graviton, but yeah, we had a perturbative check. What about the top level? What I mean, high energy level? Do you think something will come in this route? What I mean, to motivate the experiment, knowing the graviton is something, but to put an ingredient about the quantum gravity research is maybe will motivate the investment and things like that. So what do you expect?
It's a very good question. No, I mean, absolutely, it's a very good question. So one direction which maybe we can think about is this, what happens to non-perturbative aspects like that, which Suat was asking me that what happens if you give up a S-matrix formulation, and can you think about the concept of time and concept of emergence of time. So that's one direction which you can definitely think about and explore, that how can we constrain via these kind of experiments. And the other thing which I mentioned, I was talking about one loop correction. Here, yeah. So suppose you modify the nature of graviton propagators. So, and there are many theories. You can have a torsion. I mean, so far I did not speak about. I know that Durmush, for instance, has worked on many aspects of modifications of gravity. There are also mimetic gravity. So there are various forms of gravity you can bring in now. And you can ask the same question, that can you measure the entanglement, and can you see any difference from Newtonian gravitational potential? And this is a very valid phenomenological question which we can all ask, that if you change something, then of course your potential will be different, your entanglement will be different, and can you really constrain it? So for instance, in f of r theory of gravity, you know how what is the graviton propagator. Of course, now the thing which you need to constrain will be the scale, what scale it is appearing. And for instance, Heidelberg group in Seattle, they have already placed very good constraints on just the Newtonian potential or the Yukawa potential. So they usually constrain this alpha parameter and this lambda parameter. And now you can ask this question that, of course, this is a classical experiment which Heidelberger has done, but now, or in Stanford people are doing. But now you can ask the question that, okay, even if I go into these parameters, is there any quantum information which I can get? Can I see the entanglement also properties for these range of parameters? So definitely you can ask these kind of questions. And just to give an example, I mean, we looked into local gravity and non-local gravity, just as an example, and you can see that the entanglement tomography is very different in these two theories of gravity. Now you can bring in other formulations of gravity as well, like including torsion. So you have new degree of freedom which is propagating. That will change the tomography. So in principle, you can also do tomography, because you see that you're doing this experiment so many times, you can even change the parameters. You can change the distance a little bit here and there, to see that if there is a change in the entanglement entropy and what is the trend of the entanglement entropy. You can compute these things eventually. So in principle, yeah, these are very good questions, and from phenomenological perspective, to probe a little bit towards the higher end.
Okay, thank you very much. The last point is, you mentioned about 10,000 times for feeling about the graviton. What about the number of measurements for these to create statistics about this ultraviolet surge? What I mean is it really still viable in terms of years of experiments, or it's just just blow-ups in terms of?
No, it's a very good question. So suppose, just to give you an example, and suppose if I think of the extreme limits. So suppose if I perform the experiment in 1 second, and in a day I know that, and if I keep repeating this experiment 1 second, 1 second, and within a day I know how many experiments can I do, and if I compute it in 365 times 24 into 3600, I mean, I would say 10⁴, 10⁵ times I can do the experiment continually. And out of those 10⁵, there will be some experiment which will be completely worthless, because there's no, I mean, there are fluctuations, there are maybe systematic errors. So if you want to build up your confidence, you really need to do this experiment for long term. And that depends also on the phase. I'm assuming order 1 phase. Suppose you say that I'm happy to measure 0.001, 10⁻², 10⁻³ phase. To build enough statistics, you have to do even longer. So you see that there is a price to pay whenever you do this kind of experiments. And I mean, just with one experiment, you cannot, you may say something, but there's no confidence level for such experiment. So, then you cannot satisfy that, yeah, it is classical or quantum, that you cannot satisfy. That's one of the reasons we cannot go into space. Like many people have asked this question, that what happens to LISA? LISA is it will sit in a very cold part of the, universe. But can I do this experiment in a LISA kind of like system, where even free fall is, is much better? But again, it is very hard. Part of the reason is that I will not be able to build the systematics. Sorry, I will not be able to build the statistical confidence level. And if something goes wrong in space, then my $1 billion experiment is a failure. So that's why it's better to do the experiment underground, where you can do these experiments. You can build a network. Of course, these experiments will be expensive. I do not know whether it will even happen even in my lifetime, but if it happens in my lifetime, it's a big achievement. But the technology is there. In our lifetime, if it happens, it will be wonderful, because the technology is inching towards it. But there are many pitfalls. But these experiments require this kind of pitfalls. Even take an example of LIGO experiment 30 years ago, 40 years ago, what it was and what it is now. It took 40 years to build a powerhouse for measuring gravitational waves. So it took a long time. And now we are in the quantum domain. It will take perhaps something, maybe not 40, but 20, 30. I'm hoping that we can do this experiment, say, in 20 years' time.
I hope. Yeah, nice.
So,
thank you. Thank you very much for the answers. Thank you.
Any other question? Yeah. Well, it seems there is no more. So, Anupam, we can stop here. Thanks again for having time for such a very nice talk. Yeah.
Thanks. Thank you very much, Suat. And it's a really nice discussion. Many of you have asked wonderful questions. So thanks for every input, because these inputs are always very valuable. And I think, so I mean, I do not know if maybe even Turkish agencies will be interested in these kind of endeavor. That will be fantastic in future.
Yeah.
We need international cooperation.
Yeah, we need. Yeah.
See you, Anupam.
See you. Thanks.
So, Anupam, thanks again. See you.
Thank you very much.
Take care.